This is part two for us in dealing with the moles. And we were dealing with a dozen to see what that problem solving was all about. Well, the problem solving is very, very, very similar. The reason why we're using a mole instead of the number 12 is because atoms are very, very tiny. There's no way for us to use 1 dozen atoms. There's just no way for us to be able to even see 1 dozen atoms. So we need a much larger number. A guy by the name of Avogadro came up with a very large number, and it's a very, very unique number. The number is 6.022 times 10 to the 23rd. It's called Avogadro's number. A lot of times we'll just use three significant digits, the 6.02 times 10 to the 23rd. Now, what's so special about this number? Well, it turns out this number is large enough to convert all of the atomic masses on the periodic table into grams. Now, we're going to take a look at what this means in a moment. But it's an extremely large number, large enough for us to see the result of taking that many of those atoms. Let's see what this is all about. So here's our periodic table. We're very, very familiar to it. This is going to be like our bakery. We went to the bakery in our previous video in order to figure out the cost for everything that was in the menu, like baguettes, cupcakes, cakes, whatever. Well, it turns out our periodic table is like our own bakery. It tells us the amount of grams that's in 1 mole. So the number 1 mole will never change. That's always 6.02 times 10 to the 23rd. Just like the dozen is always 12. But the cost for the item was different in our store, right? 1 dozen of baguettes was $18.50. But of cakes, 1 dozen was $125. So the cost in our store was different. Well, what's the analogous situation then to the mole? Well, 1 mole will always be 6.02 times 10 to the 23rd, but the cost per atom is going to be different. What is that cost? The atomic mass. Carbon, for instance, is 12.011 grams if you take 1 mole of it. Oxygen is 15.9994. Sodium is 22.9898. So if I take 1 mole of any one of these atoms, that'll be equal to its atomic mass in grams. But it'll be the same quantity. So 1 mole of iron may be 55.847 grams, and 1 mole of potassium might be 39.0983. We have a different cost, but yet the same number of atoms. There will be the same number of atoms, but because iron is a larger atom, it'll have a larger atomic mass in grams than potassium. And that's the neat trick. With the mole, we're able to measure grams very quickly and figure out how many atoms we have. And that's very, very, very significant. Let's practice. So 1 mole of sodium is equal to how many atoms and then how many grams. Well, 1 mole of anything is equal to 6.02 times 10 to the 23rd atoms. And we can write that as 6.02 E23. Remembering that's how we really put it in our calculator. So what's that equal to in grams? Well, we have to go visit our bakery. Well, our bakery is the periodic table, and we got to look it up, just like we did in the bakery. Well, that's 22.9898. So the amount of grams it is 22.9898 grams. Let's try carbon. Carbon is how many atoms when you have 1 mole? Well, it's still 6.02 times 10 to the 23rd atoms. And again, we can write that as 6.02 E23. But what's the grams? Well, again, we got to go to our bakery, which is the periodic table, and look it up. That would be 12.011. Okay, and we can write that, and there's actually more significance to that. It's actually 12.01115, but that's good enough. Okay, so there you go. We have a way to quickly know how many atoms we have if we know the mass. Let's try a couple of questions to help us discern how to do this. How many grams of sulfur are in 3.2 E23 atoms? And then 34.4 grams of sulfur is equal to how many moles? Well, let's do the bottom question first. This one has the word mole in it. So then we know that this is going to be a one-stepper. Just like the ones above, or the other movie when we dealt with a dozen. If it had the word dozen in it, we know it's going to be a one-step question. Okay, so we got moles here. And I'm going to put 23.4 grams of sulfur here. Okay, I know the word 1 mole is going to be on top here automatically because I need moles. Okay, because the equal sign is going to say, "Halt, are you moles?" You say, "Well, yes, I am." Okay, but now I need to get the cost, okay, per 1 mole of sulfur. Well, let's go back to our periodic table here. And it looks to me like sulfur is 32.06. So let's go ahead and do that. We're going to put 32.06 here. So it's very similar to our dozen. We have to go to the periodic table, which is analogous. We're calling that our bakery. We're going to take 23.4 divided by 32.06. Anything that's on the bottom will be divided. Anything on top is multiplying. Okay, and it looks to me like our answer comes out to be 0.730 moles. Now again, it's very similar to like our dozen. Our dozen is like 7.3, or our dozen was 12. And we'll see how all this works. Okay, so let's go ahead and write that answer in. So I'm going to make that 0.73, okay, for our answer. So 0.73 moles. Okay, and that's how we do these kind of questions, okay? Let's look at another one. How many grams of sulfur are in 3.2 times 10 to the 23 atoms? Okay, well, again, we're going to need to draw our bridge, just like we did before. Okay, but now the word mole does not appear in this. So I need to multiply, okay, this one by a two-step question here. There's going to be 2 steps in here. Okay? And equals. And on this side, we're going to say grams of sulfur. Okay? On this side, we're going to put 3.2. Okay, and E 23. And again, that's for atoms. Okay, so now we have a 2-stepper here, and what you need to do right away is put 1 mole here. Okay, so we're going to write the word 1 mole automatically here. And on the bottom, we're going to do 1 mole also. Just like this, immediately, just like we wrote dozen on top and bottom before. All right, now when we look at this, now again, this is atoms here, and I'll just abbreviate that as AT for atoms, just to save a little bit of space there. AT, atoms. Okay, well, I know this is a very large number, so this has to be associated with the 6.02. Okay, times 10 to the 23rd. Because that's how many atoms are in 1 mole. So I can quickly do that. Okay, so I'm going to type in 23 here. Okay, and I'll write atoms here. Again, I'm abbreviating that as AT. Okay, there you go. All right, now, again, when we get to here, we have to go to the periodic table, which is our bakery, and we already know what that's equal to. So that's 32.06. So I'm going to write 32, okay, 0.06, and that's going to be grams, okay, of sulfur. So mathematically, what am I doing? I'm taking 3.2 exponential 23 divided by 6.02 exponential 23, and then timesing that by 32.06. So let's see what this turns out to be. So I'll take 3.2 E23 divided by 6.02 E23 equals, and I'm timesing that by 32.06. And this comes out to be about 17.0 grams if we rounded it to 3 significant digits. So we see that the problem solving is very similar to what we've been doing, okay, with a dozen. Okay. All right, I'm going to ask 2 more questions here. We have phosphorus here. So 53.6 grams of phosphorus is how many atoms? 2.4 moles of phosphorus is equal to how many atoms? Okay. I want you to try these 2. Pause the video, okay, and when you're done, double check and see if you got the right answers. All right, now it's time to see how you did. So did you take 56.3 grams of phosphorus and then times it by 1 mole over its atomic mass, 30.974 grams, and then times that by Avogadro's number, 6.02 exponential 23 per 1 mole, you get 1.09 exponential 23 atoms of phosphorus. And the bottom one, did you take 2.4 moles and simply times that by 6.02 times 10 to the 23rd per 1 mole? Hopefully that's what you did. There's a worksheet that follows both these videos. And of course, you can ask me questions as you need.